So it's useful to be able to obviously find the solutions to equations, which is what a root of an equation is when there's an equal 0. But there are some things like, I don't know, x cubed plus x equals 4 or something. I mean, they can be tricky. So we have ways of estimating or approximating. The most obvious way is halving the interval. So if you know you've got some function, key is, of course, the curve needs to be continuous. And if we know at one point it's positive and another point it's negative, and it's continuous, well, somewhere in between it must cut the axis, and there's your solution. Right? So the function a there is positive, function b is negative, so somewhere in between a and b there must be a solution to this function equaling 0. So all we simply do is halve the interval. We'll say, okay, well, we'll estimate it halfway. So let's try it with this one. X to the 4 plus 2x minus 19 equals 0. We know there's a solution between 1 and 3. Okay? So there's our function. Function 1 is negative 16, which is negative. Function 3 is 68, which is positive. So yes, there must be a solution because it's a polynomial, so it's continuous. So I'll average them out and I'll say, okay, it's 2. Sub in 2 doesn't work, it's 1. But 1 is positive. So now I can narrow it down because now I can say, well, hang on, there's our number line. I knew 1 gave me a negative value, 2 and 3 gave me positive values. So therefore, the solution now is not between 1 and 3, but between 1 and 2. And then I can halve that interval. So my next approximation is 1.5. All right, well, that turns out to be negative 10.9, so that's even further away. But what I do know is 1.5 gives me a negative number. So if I plot those on the number line, so now I know the solution must be between 1.5 and 2. So I'll find the middle of that. 1.75. Let's see if that works. No good. Negative 6.12. So let's try that again. Aha! We're in between 1.75 and 2. 1.88. Notice these, I'm rounding off to 2 decimal places because they said they only wanted the answer to 2 decimal places. Minus 2.75. No good. But now I know it's in between 1.88 and 2. So my next approximation will be 1.94. No good. Okay, well, we'll try again. So my solution will be in between 1.94 and 2. 1.97. Oh, that's so close. Now, yes, the answer to 2 decimal places is 0, but that's not what they want. They want what you substitute in accurate. So, all right, 1.94, 1.97 and 2. We're in between 1.94 and 1.97, 1.96. 1.96, negative 0.32. So we now know the solution's in between 1.96 and 1.97. So which one is it? 1.96 or 1.97? Because in the middle will be 1.965, and to 2 decimal places, that's 1.97 either. So one of those must be the answer. How do we know which one? Go to one more decimal place, and we'll find out which one it's closer to. 1.965 gives me a negative number, so therefore it's closer to 1.97 than it is 1.96. So to 2 decimal places, we have a solution to our equation, 1.97. Right? Now, that obviously took, how many steps did we go? 7, and then we had to halve that again. So 8 times we halved the interval there. Obviously with computers and spreadsheets, you can do that very, very quick. And that idea can find a solution quite rapidly. In a test, they're not going to ask you to do it 8 times. They'll probably just say, oh, we'll use one application to come up with a better estimate or something like that. Because all they're really interested in is, do you know the method? Do you know it works? This one's even better. Newton, oh, what a bloke, eh? So many things. Where would we have been without Newton? Newton's method of approximation. Okay. Here's the idea. Now, the thing with Newton's method is the first approximation needs to be good. And if it's a good first approximation, it will find the solution very rapidly. And what it does, let's draw in a curve, is it gets its approximation, and let's say there it is at x naught. At that x value, we draw in a tangent, and then the x-intercept of that tangent will be the next approximation. So if you choose x naught well, you'll get very close to the approximation quite quickly. Okay. Now, there's one where we say is a pretty bad approximation. If you happen to choose a stationary point, you're in trouble because the tangent is horizontal and it will never cut the x-axis. So you've got a problem. So, all right, we don't want one of those. Oh, and the other side of the stationary point, if I pick one over here, again, it'd find a solution. This is going to the wrong one, not the one we're looking for. Okay. So, all right, slope of the tangent. Let's work it out where x1 is. Slope, point slope formula, function x naught minus naught, x naught minus x1. So there is our solution. Okay. Put it into the point slope formula, and there we go. You don't have to derive that each time. Okay. That rearrangement, which basically comes from the point slope formula, because all we're doing is finding where the tangent cuts the x-axis. So the next approximation will be your original approximation minus the function value on the slope. The slope's on the bottom. That's what people get often wrong. But remember, if it's 0, it's not going to work. So that's how you remember the derivatives on the bottom, because you can't put 0 in the bottom of the fraction. Then you just keep going and going and going until you get to your approximation. So and the nth plus 1 approximation, we get the nth approximation and sub that into the formula. Let's do the same question. Let's see how quick. Pretend we don't know the answer. We've got to find a good first approximation, though. I'm going to choose 1.5 as my first approximation. But notice we need the derivative. So how did I pick 1.5? Because remember in the original question we said there was a solution between 1 and 3. Yes, I know it would have been logical to pick 2, but I chose 1.5. Okay? Now, 1.5, there's function 1.5. There's the derivative. Sub that into the formula, and we get 2.21. Maybe I should have picked 2. Okay, function 2.21 is 9.2744. No, that's not the answer. So work out its derivative, sub that into the formula, and we get 2. Yes, I should have picked 2 as the first approximation. Sub in 2, the function value is a nice neat 1. And the derivative is 35. Sub that in, and we get 1.97. Hence why I didn't pick 2. Because it went straight to the right answer, but I was pretending I didn't know the right answer. I just wanted to do it a few times for the sake of the example. Yes, in reality, I would have picked 2 and I would have got the answer straight away. But I don't know that's the answer, remember? So 0.001, very close. There's the derivative. Sub that in and, oh look, that's also 1.97. So I'm pretty confident the answer is 1.97 now because I just keep subbing in 1.97 and getting 1.97. 1.97 is the answer. Okay. So, we can use this to do things like that. Approximate the square root of 23. All I need is an equation, and I know its solution is the square root of 23. Oh, well, x squared minus 23 equals 0 would give me the solution. So, that's going to be my function. My derivative then is 2x. This time I've decided to create a formula. So I've actually substituted into Newton's method the function. So on the top I've got the x squared minus 23. On the bottom I've got 2x. I need a first approximation. Well, a logical first approximation to the square root of 23 would be 5. Because I know the square root of 25 is 5. And 5's close to 23. Yes, I did. I picked 5. So if I sub 5 into this formula I've created, I'll get 5 squared plus 23 on 10, 4.8. Sub in 4.8, 4.795833333333333333 goes on forever, you know. So to 2 decimal places, I'm pretty confident the square root of 23 is 4.80. Now, some other problems that might occur. You might get oscillating approximations. If you happen to be unfortunate enough to do something like this, there's our graph, and I want to find that particular solution. And so I pick x1 to be there. Okay, so there's x2. So I'm going to draw down, and I'm going to have a problem because x2 gives me x1, x1 gives me x2, x1. So you can get unlucky. So if that happens, obviously change your approximation. That's not going to work. Okay. As I was mentioning before, if you picked on the wrong side of the stationary point, it's going to converge, technical maths word there, to the wrong solution. So there's a graph. Say I wanted to find that particular solution, but I happen to pick over there. Well, the concavity of the curve is going to send me in the wrong direction. Okay. All right, handful there to have a go at.